Swayam Prabha. Digital India. Educated India.
So, the plan for these lectures, so I am going to start with, so the goal is going to look at geometric optimization problems. These problems are typically NP hard, and so what we are going to look for is good approximation algorithms for these problems. Now, there are several techniques. So, I will tell you, I will define what approximation algorithms are. There are several techniques to design approximation algorithms, and also for geometric problems, but we are going to focus specifically on two kinds of techniques, right. So, one is based on linear programming, and the other is based on what is called local search. So, the first three lectures will be on linear programming based approximation algorithms for geometric optimization problems, and the next three lectures will be on local search. Okay. So, I will define all of these things. So, linear programming is the following. Some of you might have seen it already. So, it is the problem of maximizing or minimizing a linear function subject to linear constraints. So, what does this mean? It is best to give you an example. So, let us say your problem is the following. You want to maximize x1 plus x2 subject to the constraints minus x1 plus x2 is at most 1, 2x1 minus x2 is at most 5, let us say x1 plus 3x2 is at most 9, x1 is at least 0, x2 is at least 0. Okay. So, this function here is called the objective function. So, this is the value the value of we want to find x1 and x2 such that the value of this function is as large as possible, because we want to maximize. Okay. But the values x1 and x2 must satisfy the following inequalities, and these are called the constraints. So, these are also constraints, but these are a special type of constraints. These are called non-negativity constraints. Okay. So, general linear program is the following. You want to maximize or minimize a linear function. So, you could have, for example, values here 3x1 plus 4x2 etc. But it is a linear function that you want to maximize or minimize subject to some linear constraints. Okay. Now, I will not be able to do justice to the entire theory of linear programming. We will just see what we will just take what we require from linear programming for our purposes. Now, it is easy to see that you can transform a maximization or minimization. You can transform the problem to one with equality instead of inequalities, and also if you do not have you do not want to impose non-negativity constraints, you can transform the problem into one that imposes non-negativity constraints. So, there is a certain standard form in which you can write every linear program. Okay. And let us ignore that for now, but geometrically let us see how this looks. So, these are only two variables. So, we can actually plot it. Minus x 1 plus x 2 I guess looks something like that, and all the points minus x 1 plus x 2 less than or equal to 1 is that half space. Okay. Now, 2 x 1 minus x 2 equal to 4. Okay. So, this is 2 x 1 minus x 2, this is equal to 5, this is the line, and this is the line x 1 plus 3 x 2 equal to 9. Okay. So, this is roughly how this looks, and then you have the non-negativity constraints x 1 and x 2 are positive. So, the points that can satisfy what we want is points that satisfy all of these inequalities simultaneously. So, the point should be below the blue half space, it should be below the blue half line, below the blue line. So, should lie in the blue half space, should lie in the red half space, should lie in the purple half space, which is guess that, and should lie in the black half spaces. So, it should lie in the intersection of all of these half spaces, which is this region. Okay. And this is called the feasible region. So, the set of points x 1 and x 2 that satisfy all of these inequalities simultaneously is the intersection of these half spaces, which is a convex set, as you have seen in the previous lecture. Okay. And what we want to do is to maximize x 1 plus x 2. Oh, the red one should be flipped. Ah, sorry, yes. Yeah, okay. So, what we want to do is to maximize x 1 plus x 2, which is maybe some line like this, right, and the value of, so if this is the line x 1 plus x 2 equal to b for some b, then the value of the objective function here is this point. So, we want this value to be as large as possible. We would like to move in this case as much to the right as possible, and the optimal solution here I guess lies at this point. Okay. A linear program is a problem of minimizing or maximizing a linear function. The feasible region for a linear program is the intersection of half spaces, because these inequalities give rise to half spaces. The intersection of half spaces is a convex region, and what we want to is to minimize or maximize a linear function, right. So, you can think of the linear function as moving intersecting the convex region, and what you want is if you want to maximize the point where the objective function value is as large as possible, but it still intersects the feasible region. So, this is the linear programming problem. Okay. So, more generally we can write let us just call it LP for short. We want to, let us say, maximize let's say C1 x 1 plus C2 x 2 plus Cn x n subject to A11 x 1 plus A12 x 2 A1 n x n is at most B1 and so on, AN1 x 1 plus AN2 x 2 Bm, and let us say x 1 x 2 to x n is non-negative. Yeah, we can write it in matrix vector notation as maximize C transpose X subject to A x less than or equal to B, x non-negative, where x is in Rn, A is in Rmm, C is in Rn, and B is in. Yeah. So, this is the general linear programming problem. Okay. So, what can happen? So, I am so if you have a linear programming problem, what you could have, like in the previous example with the objective function x1 plus x2, we saw that the optimal solution is this vertex. So, there is a unique optimal solution in this case. Right. So, you should take my word for it. We have not actually solved these equations by hand. Pictorially, it looks like this is the optimal solution, and let us believe that that is true. Okay. So, there is a unique optimal solution for this program, but is that always the case? That is not true. What can happen is various situations. There is a unique solution. There are finitely many solutions, yeah, or there could be no solutions. Right. So, let us look at the situation where there are infinitely many solutions. If we go back to this picture, instead of trying to draw it again, let us go back to this picture, and let us suppose that the objective function, if the objective function is x1 plus 3x2. Okay. So, we modify the objective function, instead of x1 plus x2, we modify it to x1 plus 3x2. Now, what happens is that the objective function becomes parallel to this purple line, right. So, the objective function becomes parallel to the purple line, and so as you try to move the objective function, all the points on this purple line give you the same value, and there are infinitely many solutions possible. Okay. So, that is one example where you have infinitely many solutions. It could also be that there are no solutions, and that is quite easy to construct. So, let us say, let us try to construct a linear program with no solutions. Right. So, let us say you want to maximize something x1 plus x2 subject to the constraint that let us say x1 greater than x2 plus 1 and x1 less than x2 plus 1. Of course, this is infeasible, right. You can't satisfy both these constraints simultaneously, and there is no solution. Geometrically, what happens is what you saw in the last lecture. The intersection of the convex hulls is an empty set. Okay. So, we are just looking at the whole thing from an algebraic point of view. So, let us look at, so okay. So, why is linear programming so important? So, linear programs are important primarily because you can solve them in polynomial time. Okay. Polynomial time in the number of constraints, the number of variables, and the number of bits required. Okay, so let me Sorry. Yes. Huh? Okay, let me make it loud. Okay, you want to you can solve linear programs in polynomial time in the number of constraints. This is bigger and this is better. Okay, number of variables and the largest value in these A and B. So, it is not strongly polynomial time. The running time depends on the size of the numbers in the constraint matrix or in the okay. However, for our purposes, the kind of linear programs that we will see will have very small values in the entries of the constraint matrix, and therefore, our algorithms will run in polynomial time. So, it was a big open question whether linear programs can be solved in polynomial time, and Khachiyan, I think in around 79, gave what is called the ellipsoid algorithm. This was the first polynomial time algorithm, but this was impractical. Nobody uses it, it runs extremely slowly. Okay. What was known before Khachiyan's time was the simplex algorithm of Danzig around 48. So, Danzig is known as the father of linear programming. So, he invented the simplex algorithm, but this unfortunately runs in exponential time in the worst case. Okay. The simplex algorithm can take exponential time to complete. However, in practice it is blindingly fast. Okay. So, and it is still variants of the simplex algorithm are still used widely in practice, although theoretically there are examples where the algorithm can take exponential time. Okay. And Karmarkar, I think in 84, came up with what is called the interior point method, and the interior point method is both polynomial time and fast. Okay. So, there are three ways to solve linear programs. There is the ellipsoid method and the interior point method, which are both polynomial time algorithms. Interior point method is fast, the ellipsoid method is not practical. The simplex algorithm runs in exponential time, but is eminently practical. Okay. So, there are other advantages, however, theoretical advantages of Khachiyan's algorithm, in that the number of constraints could even be exponential, and in some cases even with exponential number of constraints you can still solve the problem in polynomial time. Okay. So, we will not go into all these details. So, we just want to know what linear programs are and the fact that linear programs can be solved in polynomial time. Okay. But the problems we are going to be interested in solving are not linear programs. So, we will be interested in okay. So, what we are interested in solving are discrete optimization problems. Okay. So, given a set of jobs and a set of machines, what is the assignment of the jobs to machines that minimize the total time? If I have students and projects, we want to assign students to projects, so that some objective function is maximized. Okay. Now, in assigning jobs to machines, you cannot fractionally assign a job to a machine, you either assign a job to a machine or not. A student gets a project or not, you can't get half a project, right. So, in discrete optimization, the variables need to take integral values, integer values. Okay. So, So, integer linear program is the same as a linear program. We want to maximize or minimize a linear objective function subject to linear constraints, but additionally the constraint we have is that the variables take integer values. So, let us take an example. Let us say you are given, I am going to take a complicated example. So, let us say you are given a graph, and what we want to do is to compute a minimum vertex cover. So, what is a minimum vertex cover? Let us take a graph. For every edge in the graph, either u or v or both are in our set S subset of V. Okay. So, we want to pick a subset of vertices, so that if you look at any edge, one of its endpoints is in the solution. Okay. So, let us look at this graph. We can pick this vertex, and it covers these two edges. We pick this vertex and it covers these two edges. We still have one edge remaining, which is this guy. So, we can pick one of these vertices. Okay. So, the red vertices form a vertex cover of size 3. Right. And what we want is to find the smallest such set, that is a vertex cover. We could pick all the vertices, and that is obviously a vertex cover, right. But you can see in this graph that no two vertices form a vertex cover. You need at least 3 vertices in this, for this example. Okay. We are going to write an integer program, an integer linear program for this problem. Okay. So, to that end, let us define a variable x sub v for each vertex v in. We would like to say the interpretation is that the variable takes a value 1 if v is going to be in our vertex cover and is 0 otherwise. Okay. This is what we would like. What do we want to do? We want to minimize the size of the set. Okay. So, if the variables take only 0, 1 values, then I can the function sum over the vertices, the x v values, gives me exactly the size of the set. If a vertex is in the set, it contributes 1 to the sum, and therefore, the sum of the x v values gives you the number of vertices in your vertex cover. The constraint we want is that for every edge, one of the endpoints is in the set. That is, that x sub u plus x sub v is at least 1 for every edge in the graph. And the other finally, the non-negativity, instead of the non-negativity constraint, what we have is the integrality constraint, that the variables take only values 0 or 1. Okay. So, this is an integer linear program, and if you could solve this problem, then you have an optimal solution for the vertex cover problem, right. Any questions? The problem, of course, is that ILP is NP hard in general, and even this specific ILP for vertex cover is NP hard. vertex cover is an NP hard problem, and if you could solve this integer linear program, you would have solved vertex cover. Okay. Okay. What now? The problem is NP hard. You don't have polynomial time algorithms unless p equal to NP. So what do we do? So our goal is to look for approximation algorithms. Okay, which means that we give up on trying to find an optimal solution. We want fast algorithms, algorithms that run in polynomial time, but can give you a solution that is good, not the best, not the optimal solution, but something that is guaranteed to be good, right. So an algorithm that runs in poly time and produces a solution whose value is guaranteed to be close to opt, which is the optimal solution. So we use, let us use opt to denote the optimal solution. We will abuse notation and use opt also to denote the value of the optimal solution. Also the set, opt will denote both the set of vertices in the vertex cover, minimum vertex cover, as well as the value, the number of vertices. Okay. So more formally, so we want to design an algorithm A that is an alpha approximation for a problem pi. In this case, pi could be the vertex cover problem. So let me move that. So algorithm A is an alpha approximation for a problem pi if for all instance I of pi, if you take any graph, I feed any instance of a graph to this algorithm, what it will produce is a solution, produces a solution. So let us call it S, such that the cost of the solution S, which is in this case the number of vertices in the vertex cover returned by the algorithm, right, is at most alpha times the optimal solution, right. So this is for minimization problems. For maximization problems, you would want that the cost of the solution is at least, let us say, some 1 over alpha times the optimal solution. So at least half as large as the optimal solution. And for minimization problems, you want to say that it is no more than, let us say, 2 times or 3 times the optimal solution. But this number, this quantity alpha need not be a constant. Okay, it could be a function of the size of the graph, right. So how much time? No, how much time do I have left? Half an hour more, right? Okay. Okay. So this quantity alpha need not be a constant. Okay. So it could be a function of n. We want, let us think of just a minimization problem. We want alpha to be as small as possible, as close to 1 as possible, right. So if we could come up with an algorithm that runs in polynomial time, the vertex cover is a minimization problem. We want to pick the smallest number of vertices possible, so that for every edge one of the 2 endpoints is in our set. We can't get the best solution, but maybe we want a solution that is, let us say, better than is guaranteed to give you a set of vertices that is, let us say, no more than twice the optimal solution. Yeah. So if the optimal, if there is a vertex cover of size 100, I guarantee that the algorithm will produce a solution that is no more than 200. I am not going to give you 500 vertices and say look, here is the vertex cover when there is a vertex cover of size 100. Okay. So, this is the guarantee that the algorithm gives you. Okay. So, tomorrow if you could come up with an algorithm which is, let us say, 1.5 times the optimal, then it is even better, because you are guaranteeing an even smaller solution compared to the optimal solution. Okay. So, when you are designing an approximation algorithm, there are two steps. Of course, you will design the algorithm, and you will want to prove correctness, in the sense that the algorithm, for example, in this case guarantees to give you a vertex cover. It is not going to produce some subset of vertices that is not a vertex cover. Okay. And then you want to prove the approximation guarantee, right. You want to prove this condition, that the cost of the solution is no more than alpha times the optimal solution. Yeah. So, this is that the cost of the solution is no more than alpha times opt for all instances of the problem. For every graph, it is true that this inequality holds for that instance. So, this opt of this instance. Okay. How do you do this? The second part is tricky. Why? I want to show this inequality, but I have no idea what the optimal solution is. Right? You want to prove that this is no more than alpha times the optimal solution, but you do not know the optimal solution. How do you show this inequality? So, there are many ways to do it, okay? And there are many techniques to design approximation algorithms. Let us look at just one kind of technique. So, then let us look at the vertex cover problem again. Minimize sigma x sub v, v in v. You have that xu plus xv is at least 1 for all uv in E, xu is in 0 1 for all u in V. So, this is our integer linear program, which is NP hard, but we know that linear programs can be solved in polynomial time. I want to use the machinery of linear programs to solve this problem. So, what we will do is bravely drop this constraint and just write x sub u should be in the interval 0 to 1. So, now we have obtained a linear program which is called an LP relaxation of the integer program, right. So, all we have done is drop the constraint that the variables should take integer values and just said, well, let it take fractional values. Why is it called a relaxation? Any feasible integer solution is also a solution to the LP relaxation. So, feasible integer solution, which means any solution to the integer program, is also a solution to the linear program. It is easy to check, because the integer program wanted that the variables take values either 0 or 1. The linear program says, well, I am happy as long as the variable takes a value, any value between 0 and 1, including 0 and 1.
So, here when the xu is taken in the interval 0 1, the solution will be always in between 0 1. So, how it can be integer? Then you write.
It need not be integer. So, that is what. If you give me an integer solution, that is feasible, right. One feasible solution is to take all the vertices in your vertex cover. So, I can set x sub u equal to 1 for all u in V. Now, this is feasible for both the integer linear program and the LP. All I am saying is, if you had a solution that is feasible for the integer linear program, then it is feasible for the linear program, because the linear program says that I am happy with any value between 0 and 1. However, the optimal solution for the linear program to the LP relaxation, how does it look compared to the optimal solution to the integer program? So, what we have said is, if for the integer program, if any solution is feasible, then for the linear program it is feasible, not the other way around. So, what can you say about the relation between the optimal solution to this relaxed linear program and the integer program that you want to solve? It should be at most, right? So, every solution for the this is the key thing. Every solution to the integer program is also feasible for the linear program. Therefore, if you take the optimal solution for the integer program, that is also a solution to the relaxation, but need not be the optimal solution for that relaxation. The optimal solution for the linear program could be strictly smaller. Yeah. So, the optimal solution, any solution to the what do we know? Any solution to the integer program is a solution to the linear program. Therefore, if you take an optimal solution to the integer program, that is also a feasible solution for the linear program, but need not be an optimal solution for the linear program. The linear program could have a solution that is strictly smaller than what is achievable by the integer program. Let me give you an example. Okay. So, let us see if I can copy. Oh, this is okay. I have to write it. So, let us say I write it again. Let us take this graph, a triangle. I can assign a value 1/2 to every vertex. Okay. The linear program says that the XU values are between 0 and 1, therefore, I can assign 1/2 to every vertex. Now, look at this constraint. It says that if you add up the values to the two endpoints of every edge, they must sum up to at least 1, which is true here, and therefore, every constraint is satisfied, and this is a feasible solution to the linear program. What is the value of this? In fact, this is optimal. You can show this is 3/2. 3 times 1/2, 3/2. But what is the optimal solution for the integer program? So, this is the optimal solution to the linear program. I mean, I am claiming it is an optimal solution, but it is a feasible solution to the linear program. Yeah. So, okay. So, let me say that. So, there is a solution of value at most 3/2 for the LP. Okay. I mean the LP relaxation, but I will not keep writing it. Yeah. But what is the optimal solution for the vertex cover problem? 2. You need 2 vertices, right? You pick this vertex, it covers these 2 edges, but then there is this one edge which is uncovered. So, you have to pick one of the 2 endpoints, and therefore, the optimal integer solution is 2. There is no solution of size smaller than 2, but the linear program gives you a solution that is strictly smaller, right? It is at most 3/2. Well, I just picked values 1/2 to every vertex, and that is feasible for every constraint, right. So, in this example, I can show you, this is a simple example, I can pick values and I can show you that there is a difference between the optimal solution to the linear program and the optimal solution to the integer program. Okay. So, geometrically what is happening is this. So, if you think of the integer lattice, the integer linear program is asking for an integer point that maximizes an objective function, which is this point, but if you relax it and you write a linear program, what you get is this polytope, is this convex region for which the optimal solution lies, let us say, here, right. So, this is what is going on. So, the integer program could have a value that is strictly smaller. Okay. So, for maximization problem it is the reverse, but let us just stick with minimization.
How to get the optimal solution? You know the optimal solution. You have to guess it when developing an approximation algorithm.
Okay. So, that is good, a good question. So, now the question is how do you show, so now you have, so how do you obtain, how do you design an algorithm and show this approximation guarantee when you do not know the optimal solution. Okay. What we have is the optimal solution of the linear program is strictly smaller than the optimal solution for the, or is at most the optimal solution for the integer program, which is what we want to solve. So, therefore, what we will do is a technique called LP rounding, which is that we will, the technique is this, solve the linear program, which we know we can do in polynomial time. So, I mean the LP relaxation. Yeah. So, you are given a discrete optimization problem, you write an integer linear program, you relax the integrality constraints to get a linear program, and you can solve the linear program in polynomial time, right. Okay. So, you have the solution to the linear program, and now what we want is to use this fractional solution. So, from the optimal solution to the LP, what we want is a solution that is integral. Yeah. So, you want a solution, you want to produce a solution. So, the LP is giving you some clue, right. I mean, it is saying you, well, you should take this vertex with x value at least, let us say 3 by 4 or at least 0.9. That means that maybe it is a good vertex to pick, right. So, you want to use the information from the LP to produce an integer solution. Okay. But you want to do this without losing much. Okay. So, what does that mean? You have the optimal solution to the LP. What we are going to do is to produce a solution S, okay, so that the cost of S is not much more than the cost of the LP. So, cost of S is at most alpha times the optimal solution to the LP. But what do we know? We know that opt LP is at most opt. Therefore, this is at most alpha times opt. So, we are going to do this in 2 steps. What we are going to show is that the optimal solution is alpha times the, so the solution we produce by taking the fractional solution to the linear program and rounding up the values in some careful way is at most alpha times the optimal solution to the linear program. So, we are showing something stronger. But we know that the optimal solution to the linear program is a lower bound on the optimal solution to the problem, and therefore, it is alpha times the optimal solution to the problem. So, this is what we are going to do.
So, what is integer case given?
Sorry?
Integer, but integer case.
We want a solution S that is integral. In the sense, so what do we want? We want the x values to be 0 or 1. We want to pick all the vertices. I want to know which vertices to pick. What the linear program is doing is giving you fractional values to the vertices. You want to you might interpret that. So, I am going to do that now. I will show you how you can do it. That is called LP rounding. So, I will show you an example, 2 examples, vertex cover and set cover. Okay. So, we have the fraction solution, we want to somehow carefully round it to get an integer solution. You might want to
that integral solution is an optimal solution.
is not, it need not be an optimal solution,
Then how can I prove the approximation algorithm is alpha?
which is what we want to do. We want to prove that the solution, the integer solution that you obtain from the linear program is at most alpha times the optimal solution to the linear program.
Optimal solution to the linear programming with the integrality function.
No, no, no. Let me do it by example. Okay, it will become clear. Okay, so let's look at the vertex cover problem. Right. So, let me give you the algorithm. Right. Solve the LP relaxation. Okay. And let us look at the LP. Okay. Let us say x is the optimal solution to the linear program. So, the linear program is the following. Okay. Pick all vertices such that XU is strictly positive. It seems like a weird thing to do. This is the algorithm. The algorithm is just going to solve the linear program, and every variable that is more than for which the LP gives you a value more than 0, strictly more than 0, just take it. I claim that you can't be too bad. No, the linear program can produce fractional values, right? So, for example, if you look at this triangle, the optimal solution to the linear program is assignment of value half to every vertex. Okay. So, now it could be that if you had another vertex like this, the linear program gives a value 0 to this vertex. In this case, it is not feasible. Maybe I can do that. But so I should change it. That's 1, and that is 0. Okay. So, I can modify the picture where this vertex has value 1 from the linear program, and this vertex has value 0. Now, this is a feasible solution. I do not know if it is optimal, but let's assume that it is true. Okay. I claim that just picking all the values with all the vertices with value that is positive is a feasible solution, and it is a good solution for the problem. Okay. So, let us give this a name. So, this is the algorithm A. A is a 2 approximation for vertex cover. Okay. We want to prove that this algorithm, the solution produced, is not too bad, is at most 2 times the optimal solution. Okay. So, how are we going to do this? It is just a simple observation. Since XU plus XV is at least 1, for every edge the sum of the 2 endpoints is at least 1. This implies what? One of these values should be at least half, right? Now, let us look at the objective function value. objective is x1 plus x2 plus and so on plus x sub n, right. So, maybe this is a set of vertices for which the LP gave you a value 1. This is a set of vertices where the LP gave you a value between 0 and 1, and these are all the vertices for which the LP value gave a 0, right. So, what our algorithm has done is to pick all of these vertices in our solution. Okay. Okay. So, now can you see why this is a 2 approximation? So, I claim that what this algorithm has done is produced a solution, let us say x 1 prime, okay, let us say y 1 plus y 2 plus and so on plus y 7. So, every vertex has now y i's are either 0 or 1. Okay. We want to prove that sigma y sub I is at most 2 times sigma x sub I, right. So, let us say this produces a solution y 1 y 2 up to y sub n, where y i's are okay. Is this clear so far? So, what we produce here is an integer solution. So, the y i's are the integer solution, it is 0 or 1.
So, the solution of the fractional solution of the relaxation problem can be set as a the information to find the upper bound of the optimal solution.
Yes, a lower bound of the optimal solution. Yes. So, you are using the lower bound produced by the LP to obtain a solution from it to obtain a solution to the integer program. Yeah. So, why is this? Each xu. So, the observation is that since xu plus xv is at least 1 for every edge, then one of these is true, either xu is at least half or xv is at least half. Okay. So, let me modify this. Sorry, I made a mistake. This doesn't go. Okay. Sorry. So I pick each vertex where xu is at least half. So I wanted to show something else. Okay. So pick each vertex with whose value is at least half. Okay. Okay. So then either xu is at least half or xv is at least half. Okay, I've not. Let's do it this way. Do it again. So I made a mistake. So the algorithm is to pick every vertex whose value is at least half. Okay. The previous algorithm will also work, but for a different reason. But so each variable is at least half. Now, since every vertex for every edge the constraint is xu plus xv is at least half, is at least 1 of xu or xv is at least half. So, for every edge at least one of the endpoints is chosen in our solution, right. So, the algorithm is to solve the linear program and pick every vertex whose value is at least half. Okay. If the LP gives a value at least half, then you take it, otherwise you do not take it, that is what you do. Okay. Now, first of all I want to claim that this is a feasible solution. Why is it a feasible solution? Look at an edge, xu plus xv is at least 1, that is the constraint that is satisfied by the linear program. So, one of these vertices has value at least half, and if it is at least half, then we will take at least one of the endpoints, which means the edge is covered. So, every edge is covered by the solution returned by our algorithm. To show that our algorithm is not too bad, look at the optimal solution. The optimal solution has some variables 1, some variables between 0 and 1, and some variables 0. Yeah. So, this we look at all the variables whose value is at least half, and all the variables whose value is smaller than half, and the rest. So, what we have done is to take all of these values. So, this is our solution. Right. So, what we get is y1 to yn, which is 0 or 1, which is a solution to the integer program. So, the first set of yi's, where in the objective the LP gave a value 1, we also give a value 1. Right. Now, for these values where the LP gave a value at least half, we at most have doubled it to get 1. Right. Right. So, here yi is at most 2 times xi. Yeah. So, this is 1, here yi is at most 2 times xi, because xi is at least half, and the rest are 0. Therefore, the sum over the yi is at most 2 times the sum of xi. Right. For those for which the LP gave value 1, we also gave value 1. For those for which the LP gave value at least half, we at most double to get a value 1. For everything else, we just set a value 0. Okay. So, there we get a 2 approximation. Right. So, this is 2 times opt LP, which is at most 2 times the optimal solution. So, we use the linear program to get a fractional solution to the integer program. Okay. So, I wanted to introduce another problem, set cover, for which the rounding is not so straightforward. The rounding is more involved, but what I will do is I will do it in the next lecture. Okay. So, since I have 5 minutes, let me give you another algorithm for vertex cover, which does not go via solving the linear program at all, to show you that there are other ways to solve this problem. Okay. So, the algorithm is the following.
Sir, I have a question not related to this. Can I ask?
Yes.
Suppose I have I will say a rectangle in which I want to place some cells so that they do not overlap, correct? And I want to minimize the area, minimize the dead space, right?
Mm-hmm.
So, can it be done by this ALP relaxation?
You could write an ILP, yes. You could possibly write an ILP.
So, the objective function will be the dead space, how to minimize the dead space.
If it is a linear function, yes. If it is a linear function, or if you can approximate it by a linear function. If the space is quadratic, then of course it is not an integer linear program. Okay. So, the algorithm again is going to look strange, and we will see why this algorithm makes sense. And in fact, this is not the way to design an algorithm. What we will do is make these observations, and the algorithm has come as a consequence of all these observations. Okay. So, let S be the empty set. While there exists an edge UV uncovered, which means that neither of its endpoints have been chosen, pick both the endpoints. Okay. It seems strange, right. You just want to pick one of the endpoints to ensure that the edge is covered, but the algorithm is saying look, pick both endpoints. Okay. So, the claim is that let us again call this algorithm A. A is the 2 approximation. Okay. So, this is a purely combinatorial algorithm, there is no linear program that you are solving, right. It is just saying as long as there is an edge that is uncovered, just pick it, pick both endpoints, that is a solution. Okay. And the proof is this. Okay, I am going to sketch the proof and you can try it out later. Suppose the graph had k disjoint edges, right. Suppose in the graph you could find k disjoint edges that do not share a vertex. Okay. So, if G has k disjoint edges, then the optimal solution is at least k. I claim that if you find k disjoint, if you are able to find k disjoint edges in the graph, then the optimal solution value is at least k. Why? Because you need a separate vertex to cover every edge. No 2 edges here in this set can be covered by the same vertex. So, every edge requires one vertex. Yeah. And what have we done here? We have picked a maximal set of edges that are pairwise disjoint, right. And since we have picked both endpoints, all we have done is doubled the number of vertices we have picked is twice the number of edges here, which is twice. That is it, that is the proof. Okay. So, I mean combinatorial algorithms are preferable because they are faster to, in many cases faster, but the linear program gives you a principled way of getting a lower bound. In this case, we knew that the size, we obtained that the size of a maximal matching is a lower bound on the size of a vertex cover. So, not every optimization problem gives you such a clean lower bound, right, but linear program gives you a principled way of getting a lower bound. Just solve the linear program, we know that the solution to the linear program is at most the solution to the integer program, and then we are going to try to round the solution. There are other ways to use the linear program solution, right, to use linear programs, in particular what are called duals of linear programs and use what are called primal dual algorithms. But we will not go into that. Our goal is to just look at randomized at linear programming rounding. Okay. So, in the next lecture we will look at another problem called set cover, and then our goal is to look at how we can use geometry to improve the solutions to some of the problems compared to what we can do for the abstract for the general problem.